Why would we want reasoning at all? This is an example question. What's the total sum of peak points of the green and red lines? This is a pretty complicated image, and it does take some reasoning to find the sum. So the question is, how do we get visual language models to break this down and get to a final answer? Welcome everybody to Archive Dives with Oxen AI, where every week we dive into interesting research papers in AI, and we not only like to read the research papers, but when applicable, we like to try out the techniques ourselves. And today was one of those papers that we could kind of get our hands dirty and try some of the prompting techniques and kind of go deep on how to reproduce this type of work. And so today's paper is called LLaVa Chain of Thought, or LLaVa CoT. So high level overview, if you're not familiar with vision language models, it's pretty much just adding image to the prompt as you're going along and using these large language models. So I decided to pick a cat example here, probably not the most practical one, but you have the image and a prompt and you say, what's the cat wearing? And hopefully the LLM answers sunglasses. And while that might not be the most practical example, I made a long list here of other things that you could do with VLLMs. There's the classic, just like categorization of images. You could do things like automatic receipt reading, analyzing game footage and sports, generating captions for alt text for websites, analyzing charts and PDFs, medical imaging, navigating web pages. There's a lot of use cases here. And if you guys are doing any of this in the real world, feel free to put it in the chat so we can add it to this list and just see what people are working on. But this paper is all about adding reasoning to these visual language models. So why would we want reasoning at all? And there's a nice benchmark data set that they reference in this paper called Chart QA. And so I took an example from here, and this is an example question. What's the total sum of peak points of the green and red lines? So you can see this is a pretty complicated image with a few charts, and it does take some reasoning to find the sum of the peaks, being able to look at the X and Y axis and do some sort of summarization. So the question is, how do we get visual language models to break this problem down into subproblems and get to a final answer? So in traditional language models, there's prompting techniques called chain of thought. And here they take it a step further and they use what's called inference-time scaling. So not only do they use chain of thought reasoning prompts, but they use this thing they call inference-time scaling, which is kind of a search at inference time over all of the thoughts that the model's generating. And they have a lot of interesting benchmarks that show that this improves the reasoning capabilities. And we'll kind of dive into what the chain of thought prompts look like and what this inference time scaling is. They did release this model open source. It's available here on Hugging Face. If you want to go, just search for Llama 3.2 V11B CoT, chain of thought. That's where it is. And the two kind of main contributions that this paper makes is, along with the inference time scaling that we'll talk about, they create a synthetic data set of 100,000 training examples. And this alone, these two techniques alone, inference time scaling and the synthetic data, make LLaVa chain of thought outperform some of the closed source language models like Gemini Pro 1.5 and GPT-4o Mini. It doesn't quite beat GPT-4o non-mini, but they generate a lot of their synthetic data from GPT-4o, so that kind of tracks of it's hard to beat the model that you generate the synthetic data from. So this is another paper, another win for synthetic data. We've seen this over and over as we've looked at some of these more recent techniques to scale these open source models. And what's interesting about their technique in this paper is they have a very detailed prompt that has the model break down the problem into 4 distinct steps. So the first step is summarize what the model sees in the image. The second is create a caption for the image. The third is, given the summary and the caption, create a detailed plan or analysis or step-by-step reasoning that you can take that information from the summary and the caption, and then come finally to a conclusion. And so what this looks like in practice is if you have an image like this, this is a science problem from one of the data sets where we have like the width and the height and an equation here. And the question is, an acetyl polymer block is fixed to the rigid plates at its top and bottom surfaces, et cetera, et cetera. I won't go through and read this whole thing, but basically it's a multiple choice question to try to find the answer. And I don't know exactly what they're asking for here, but one of the people on this call definitely works with polymers and chemical stuff, Andre, so this one might be interesting to you. It's kind of why I picked it if you showed up. But what happens is they have a prompt that tries to break this down into those 4 steps. And they explicitly prompt the model to put each one of these sections into XML tags. So they have the summary section here. They have the caption section where it's trying to caption all the important information in the image. Then they have the reasoning stage, which is like, how do I solve this problem step by step? So you can see it has reasoning tags and it puts its step-by-step computation in here. And then finally, conclusion stage, it puts the conclusion into these XML tags here. And that's how they end up extracting the final answer. So the full prompt that the paper used, that's kind of looking at the output. They provide it in the appendix of the paper. Let me wrap this so we can kind of see it. But it's basically, I have an image and a question that I want you to answer. I need you to strictly follow this form. It defines those 4 sections that it wants it to go through. And then for each section, it says what it wants the LLM to reason through or provide in that section. So summary section, briefly explain what steps you'll take to solve the problem. Caption, describe the contents of the image. Reasoning, outline a step-by-step thought process you would use to solve the problem. And then conclusion, give the final answer in direct format, must match the correct answer exactly. They give some more just like details on the actual format of the response that you want. Don't forget conclusion. And then please apply this format meticulously. And so that's the whole prompt to generate the synthetic data. And if you want to grab it, we'll link it here after, and it's at the back of the paper. So given this prompt, they take GPT-4o, which has vision, and they grabbed a variety of examples from the following data sets here. So they ended up grabbing 100,000 examples from these 10 or so data sets, and you can kind of see the breakdown from each one of these data sets, how many examples they got from each. And so like that example I was showing at the top was from chart QA, share GPT-4 has a bunch of other sub data sets within it. There's science questions, there's like document visual QA questions. So wide variety of images that they collect here. And they actually don't keep any of the labeled data from these data sets. They're just like collating all of the images from a bunch of different sources so that they can run this very detailed prompt on all of those images and generate the synthetic data set for supervised fine tuning. I looked into some of these data sets, and they often just like live on academic servers in tarballs and all over the place. So I kind of took this list here. And if you're not familiar with Oxen, we're all about data sets and sharing large machine learning data sets. So I went through and downloaded a lot of these zip files and organized them and put them into this image chain of thought 1 million repository. So this has 1.2 million images. None of them are labeled yet, but they do have what source they came from and the images themselves. So there's a test set here and a train set here. And my hope was that, in this paper, they generated the synthetic data set with GPT-4o, which technically has a bunch of licensing issues. I was kind of thinking as I was reading it, well, there's other visual language models that are out there, like some of the newer Llama models. So I was thinking, like, what if we just took all of those raw images that have valid license that we can use and use a similar prompting technique, but with a open LLM that we can actually use the data from. So that's exactly what I started to do last night, and I had some interesting results. So, this is kind of the full process that we talked about here. And you can either try to put that entire prompt in that we showed above. And actually had pretty good luck with that using GPT-4o. So let's see, this is me putting in all the different data sets last night, but here's the chart QA data set. And I took just 100 examples here just to like prompt engineer my way through these steps and see how well it would work. And I have a bunch of different experiments that I did here, but let me start at the GPT-4o chain of thought so you guys can kind of see the outputs here. And so I took that exact, or actually a similar prompt to the paper. I had to do a little bit of prompt engineering here to get it in the exact format that I wanted. But if we look at the results, basically we have these pretty complicated charts. We have a labeled answer, and then you can see in this prediction column here, it generates the summary, it generates the caption, it generates the reasoning, and then it generates the conclusion down here at the bottom, and is actually pretty accurate. It got this first question correct. It got that second question correct. And so I wrote another script after this just to like compute the accuracy. And for these 100 examples, it got 57% accuracy, which was pretty aligned with what the results were in the paper. So if we scroll down here just to kind of give you guys a sense of what we're going up against. On a lot of these visual QA data sets, it's like mid 50s, and for some of the multiple choice questions, it gets up to like 75%. So I was like, cool, that prompt works pretty well with GPT-4o, but like, can we do it with a more open language model and not GPT-4o? And this is where it got interesting. I tried with Llama 3.2 11B and Llama 3.2 90B. And let's start with some of the examples from Llama 90B. Oh, that's not the one that I wanted. Let's go all the way down to the bottom here. Um, Here we go. Llama 3.2 90B. So the first thing that I noticed is it had a really hard time following the format that you specified here. Like it was just not putting it in XML tags. It was doing some of the step-by-step reasoning, and it was getting the answer correctly sometimes. And sometimes it would give the actual right XML output as well, and the right answer. But you can kind of see as we're scrolling through here, it's very non-deterministic and not as consistent as GPT-4o at following the instructions that we gave above. So computing accuracy on these 100 examples with this crazy non-consistent format that we were getting out here, I got about 11% accuracy, which was pretty disappointing, I guess, for a 90 billion parameter model here. So the next thing that I thought was like, okay, well, what if we, instead of putting all of that into a single prompt, what if we break it down into sub prompts and then generate a column per sub prompt? So like the sub prompt for the summary is just summarize the image given the query. Then a sub prompt for the caption is like just caption the image, then just provide the reasoning, and then provide the conclusion. And that actually worked really well, even with the Llama 3.2 11B, just breaking those down into separate API calls and separate prompts. And after doing all that, I ended up with like 37% accuracy for this 11 billion parameter model, at least on these 100 examples that I was kind of prompt engineering on. So what that tells me is we can at least use like these Llama 3.2, break down the problem into these substeps. And I think it would also be interesting to even generate multiple responses for the substeps, try to find the best one for each substep, and then generate a synthetic data with all of that combined. And I think you could get a pretty reasonable synthetic data set with one of these open models that we could use. Again, this was all just last night into the wee hours of the morning, but the fact that got it up to 37% on this small subset was definitely encouraging. I'll pause there for any questions on the synthetic data or like the experiments that I did. Do we have any questions in the chat, Josh?
Just one about running the models. So just wanted to point out that this was all run through Oxen hosted there, and you were using Grok for that.
Yeah, exactly. So we have this evaluations feature within Oxen, and you can kind of pick any data set here. We have text to text, image to text, or text to embeddings. And then for image to text, we have OpenAI or Grok. And then so I just picked Grok here, Llama 3.2 11B. And you can just say like, you can put in a prompt here, grab the image from the image name column, put in the question here, and maybe have a little context like answer the following question very concisely. And then we'll go run inference given that prompt and give you all the responses. And you can kind of prompt engineer here and be like, respond with one word if possible.
So Greg, what you're showing here is like a way to kick the tires on new models that is super easy. Is that correct?
Yeah, totally. So you don't have to download it, write any code. You can just like focus on your prompt engineering, and then you can kick off these jobs like on the full data set, and you can actually save the results to different files and different branches. So we could say like results
Greg, could you scroll up so I could get a screenshot just to show to tweet? Okay, cool.
Yeah, totally.
I mean, this is such a cool feature.
Yeah, I've been finding it like
that too. This is so cool. Oh my gosh.
And, I love writing code and downloading these models from Hugging Face or whatever, but just be able to kick a lot of these off in parallel and like experiment and have it running in the background without you having to manage all the jobs.
Yeah,
really helpful for me.
You like removed the annoying work.
Exactly.
Yeah, cool.
Is there a trial version or trial possible with Oxen?
Yeah. So if you sign up, we actually give everybody like $10 of compute credits to start. So feel free to just burn through that.
Yeah,
and
and I was thinking more of a trial for the Oxen framework. Like, you would have to pay for the LLM if you're using it. Like OpenAI, you should pay for it.
So we manage a lot of the internal logic there and the API keys. So we just give you $10 of free compute and you don't have to pay for it at the start.
Okay, and then if you use more, you just pay for it at that point.
Yeah, exactly.
Is it possible to use like the Oxen framework to build like, I'm going a little off topic, but to build like agentic frameworks?
Not yet, but we're definitely thinking about that. And you can hook in any data sets that we have here into agentic frameworks. So like all the data in any of these repositories, whether they're JSON files or Parquet or whatever, you can access them through APIs, download them, version them, and do anything you'd want, like in Python.
Cool, thank you.
Yeah,
this is really great.
No problem. Cool. So that was kind of like the synthetic data half, but the other interesting half of this paper is what they call the inference-time scaling. So let me scroll down in my notes here. And this is something that's kind of like debated in the community of, is OpenAI doing inference-time scaling for O1 under the hood? And in this paper, when they talk about inference-time scaling, they're actually just talking about pretty standard search algorithms from computer science. So namely, in this paper, they use beam search over the results. So if you're not familiar with beam search, we'll go over it a little bit here. And there's a great Wikipedia article. But the rumor is that, you could generate all of that synthetic data like we did above with prompting and have it be chain of thought reasoning, and then use supervised fine-tuning or DPO or reinforcement learning from human feedback on top of that. But there's rumors that OpenAI's O1 uses like this text time compute and either does like a tree search or maybe beam search or something under the hood. But it's hard for us to tell as a community. So it's been debated a lot. But in this paper, they kind of show a couple different techniques that they explore. So there's best of n search, there's sentence level beam search, and then there's stage level beam search, which is the kind of the one that they settled on in this paper. And so best of n search would be like, given a question, generate 5 different responses, and then have the LLM itself look at those 5 different responses and pick the best one. That's pretty straightforward. There's then sentence level beam search, which for each sentence that the model's generating, you actually generate 5 different sentences. And at each step there, you say, okay, which one out of these 5 sentences was the best? Pick that one, and then feed the best one into the next step, generate 5 new sentences, pick the best one, and on until you get the final answer. Since we already have in this paper those 4 stages that we talked about before, like the summary, the caption, the reasoning, and then the conclusion, they do the same process, not over just the sentences, but over those 4 steps that they lay out in the prompt. So they'll generate 4 different summaries, they'll generate 4 different captions, generate 4 different reasoning steps and 4 different conclusions, and then get to the final answer here.
Hey, Greg, we had a question about where you found out it was beam search. Was that just in the paper?
Yeah. This is
diagram?
from the paper itself. Yep. And they lay out this algorithm or these steps in the paper. And so often with beam search, you have a parameter n of like how wide you want the search to be. So you'll see in some of the results later, they say like, here are results with beam search of size 2, size 3, size 4, and basically sample n responses, randomly sample 2 responses and let the model determine which is better. Repeat this for n-1 times, and then repeat until you get to the next stage. If you want to dive even deeper, they have all of this code on this GitHub here. So it is just this LLaVa chain of thought GitHub. And the first question I asked myself is, okay, well, you're generating all these different responses for the beam search. How do you judge which one is the best? And so kind of found the spot in the code that they do that. It's this judge function. And what's interesting is you can see they have different prompts for judging depending on what type of process they were running here. So if it was the sentence level beam search, they have this prompt. It says, act as a judge, help me determine which of the 2 texts I provided is better. Next sentence for the answer to the question. Or if they're doing that method that we showed kind of on the right side here of beam search at the stage level, they actually have different prompts for different stages. So they have a prompt for the summary stage, for the caption stage, for the reasoning stage, and for the conclusion stage. And I think the idea here is you might want to give it different hints about what you mean by reasoning or what you mean by caption. So I thought that was kind of interesting, is they don't have just one judge prompt for any arbitrary part of the chain, but they had different judges or different prompts for the judge for different parts of the reasoning. So if you want to check out any of those prompts, it's all in the code there. And I actually extracted all of this and I'll put it in the blog that we follow up with as well. So let's look at an example of this beam search actually helping answer a question. And again, this is an image from the paper. And so the question is, what is the total price for a bottle of Merlot and a bottle of Cabernet shown in the image? So they're trying to extract the dollar amounts from multiple of these signs and then also have it understand which one's the Merlot and which one's the Cabernet and then add them together. So they have an example of the answer without inference-time scaling. So just generating the summary, caption, reasoning, and conclusion, and then the answer from beam search. And the answer without inference-time scaling, they say the Merlot is priced at 139, the Cabernet is priced at 109. Adding these 2 together is 149, which is clearly not the right answer of adding those 2 numbers together. It forgot the decimal, the hundreds point there, I guess. And so when you have beam search in the loop, you can get to this reasoning step and the model will predict multiple different reasoning chains. And then you can use the judge to look at all of the reasoning chains and pick the best one. So if you do that, in this case, one of the reasoning chains had the correct math in it, and then they got the right answer. So that's an example of how this all comes together, both the inference time scaling and the beam search. So what does this look like in terms of accuracy numbers? So remember before I mentioned you could have different sizes of the beam. And so this is on a data set called MMVet, which I also put up here, and I forgot to even look at what this data set was. Large scale multimodality evaluation suite. So, oh, this looks like a bunch of like handwritten math problems and questions. And so it's kind of a combination of optical character recognition and like questions. That's pretty cool. And so they say with no inference time scaling, this technique gets about 60% accuracy. With the best of n search of just generating n answers and picking the final one, they get a little bump in accuracy, not great. With the sentence level beam search, it actually goes down for some reason. And then for the stage level beam search, you get a boost of 2%, almost 3% accuracy on that test. And then so given that, they're like, okay, there's these 4 different techniques. It looks like the stage level beam search works the best. So within the stage level beam search, they also tested different beam sizes. So you can see this was the best one here, beam size of 4. But with beam size of 1, that's pretty much no inference time scaling because there's not multiple options that you can choose from. But with the beam size of 2, accuracy goes up a little bit, 3, a little more, 4, a little more. They didn't mention if they tried higher than that, but seems like 4 is a good balance of not generating infinite responses that you have to evaluate, but having a good middle ground there.
I have a question about how much slower that is, that it might not be worth the, depending on the use case.
Yeah, totally. This is a pretty expensive operation, the beam search itself. So it's definitely dependent on the number of stages that they have there. So 4, and then the beam width as well.
And I missed a question a little bit ago about whether beam search is compatible with transformer-based architectures.
Yeah, I mean, so what they're doing is they use the transformer to generate the completions, and then for each one of the completions, they kind of do the search over that. So it's compatible with like any kind of prompt response output. Cool. So model training wise, they actually used Llama 3.2 11B Vision Instruct, which was the model that I was showing in our UI a bit ago, as the starting point. And then they said they trained it on that 100,000 examples with 8 H100 GPUs. And I just wanted to do like a little back of the napkin math. They didn't say how long they trained it for, but you can rent a machine like this from Lambda Labs or other services for like $3 an hour. So if you needed to train something like this for a week, it would probably only take $500 or so, which I thought was interesting. I don't know that it only took a week for 100,000 examples, but just I like to do a little back of the napkin math in case somebody wanted to check that out. And then they not only ran it on that MMVet data set, but they did it on all these other academic benchmarks, which I actually put all of these into a collection on Oxen AI if you guys are interested. It's just this visual LLMs collection. So I have like all of the data sets that they mentioned in this paper here if you want to see the nitty-gritty details. But this approach improved on all of the baselines from the original model. So this is the base model. Hopefully it's big enough so you can see, but on average, adding both the synthetic data training and the beam search got like average of 9% improvement from the base model on all of these different tasks, which is pretty impressive across the board. So I thought that was pretty interesting. And then how does this compare to the closed source models? We showed the graph kind of at the start here. And GPT-4o at the time of this paper was state of the art in most of these tasks, and they don't quite get to GPT-4o level, which makes sense. Again, I said they generated the data from GPT-4o, so at least kind of like the top bar that you could get would be matching that performance, unless you did some human annotation or some interesting synthetic data filtering. But it does surpass Gemini 1.5 Pro and GPT-4o Mini on a lot of these benchmarks, which is pretty interesting for an open source model. So yeah, I think, the advantage of this is obviously you can now have an 11 billion parameter model that you could run locally, have full control over, do progressive fine-tuning on, and you're not beholden to using somebody else's API. So I think this is a really encouraging starting point. What I would love to see is just kind of like the experiments I started last night, but like, can we do this without using GPT-4o at all? And if you've been following archive dives, we've been doing a lot of synthetic data generation and talking about synthetic data. And I think there's techniques that we could put together to generate a similar data set, but isn't beholden to just for academic use, like you would if you use GPT-4o. So that's kind of it. I'll kill the recording here and we can kind of chat about this offline. And I'm curious if anybody's working with VLLMs in general, but thanks for joining if you're watching on YouTube, and see you next time.